let's get started. Let's get started. So, we are at a point where we've got a lot of stuff. We've got a working syntax tree. We've got a working lifting and unlifting mechanism where we can take queries and plug them into other queries. Oh, by the way, I even introduced this nice little code formatter into our printing function, where now what we could do is we could say compile it and it'll actually format the Scala code for us. So now we have the formatted code. So remember back in the day or last time where this was like this big blob, right? So now we actually can see what this thing actually is, or if you want the short version, here it is right there. So we can actually see the code that was lifted being printed. Now, so we've got this all going. What I want to do is I want to do two things. I want to start going into doing a parser, like the binary operation parser, but before we do that, I want to make this real. That is to say, I want to start using Quill proper in order to build up these trees and not use this sort of fake syntax tree that we've constructed. I want to start using the real thing. So, and then also once we've got that going, what we can actually do is we can actually plug the syntax tree into Quill and actually relatively easily have it spit out an SQL query once we've plugged in the Quill syntax tree and we're able to run the query compiler. But first we have to import it. We have to swap the syntax tree, and then we have to write a run function, right? So Quill, for example. So here's what I want to do, right? Let's take a look at a simple Quill query, right? Let's take a look at what goes on in regular Quill. 3.5.2. Let's get that. Okay, now val ctx case class person name string age int. Now let's say val q query q quote query person import ctx. There's our query. Let's take a look at AST. So this is fairly simple, but this is what we need to produce if we want to be able to do this. Right? If we want to be able to run it, we have to produce this kind of syntax tree. Well, we have something very close to this, we just have to use these classes. Also, let's do something that resembles what we've done in our example, which is q.filter p2 p.name equals Joe. Let's run q1. There it is. So there's our query, and again, q1.ast. There's our syntax tree. This is what we need to produce. Alternatively, what did we have here? We had person is Russian is human, etc., etc. So we let's say filter. Let's define val q. You have to redefine q because you've redefined person. That's the way that it works in the REPL. So there's our q. And let's redefine q1. q.filter p2p dot is Russian. Right, run q1. There it is. We're filtering it. So what we need to do is we need to, again, produce an AST that looks like, or that is this. Right? Where is this coming from? Well, it's coming from the Quill project, AST. Let's actually, let's check out the correct version of this. 352. Oops. So there's version 3 AST. There's version 352. And let's look at what we've got. Entity. There's entity. So this is pretty similar to what we've got. Let's see if we could just replace the toy syntax tree that we've implemented here with the real one here. Okay? So we could probably pull this off. We haven't implemented binary operators yet. We'll do that soon. Let's import io.getQuillAST. Okay, so here's our import. Now, let's see. There are going to be a few errors. Let's see if we could spot them. Well, actually, let's just compile. There are going to be a couple of errors. For example, when we're parsing this query entity in order to create it up, there we go, it already lined it up for us. Missing argument for method apply properties. So we are missing this list of properties. Right, we're creating an entity here. Right, we're missing a list of we're missing an args list. Oops. So we're missing this thing here. So let's just add an empty list. Again, those are for renaming things.
Oh, it's not anymore.
Oh, that's not complaining anymore. Why is this? Okay, that doesn't seem to make any sense. Let's put that there. I don't know why this is complaining, but that's odd. And then, of course, the unlifter needs to be a little different. But that's fine. We can just add that empty list in there, and then we could do case name, and we don't really care about the second argument. And for the lifting, the lifter, we had, the unlifter we had to put up. Oh, that's why it's complaining, right? Because there's a second argument.
Oh.
That's why it's complaining, right? It has to lift the second argument properly. But again, we don't care about it because we don't care about the content inside. If you actually wanted to do this, right? If you actually wanted to do this, you'd have to figure out a way to take this thing and lift it and write it back into there. And we have a way to do that. We just aren't going to do that now. Okay, expr list. Okay, so, haha, it's funny. Normally we can do this, but this actually expects... What does this expect? Entity... Oh, whoops! I put it inside of expr of name. Right? I'm swapping in the name into entity. Right? I need to have it in there. Oh, wait, no, still wrong. There we go. Now, let's compile it. It should work, hopefully. And okay. Look at that. That is the real AST io.getquill.entity ident property, right? This is the real thing now that we're working with, or close at least. So yeah, let's implement a simplified run function. Okay. Inline def run. What is run? Well, it's a macro, of course. And in this case, run is a little specialized. It is going to have a T on it, but in this case, it is going to have an inline query. It's going to be a quoted of query of T. If you look at the original Quill, run. Run. There are multiple run functions, and they are specialized towards having a certain kind of thing. So in this case, run is going to be a quoted of query. Because the run implementation for things like inserts as opposed to selects are different. So quoted of query means to select. So okay, fine. And again, ceremony run impl. It's going to be P. And this is going to be Q. And then def run impl T type quote or Q expr, right? Expr of whatever we had here. And equal, what does this thing return? It returns expr of, what should we make it return? Well, it doesn't need to return anything per se, but let's just make it return, the query, right? Actually, we want the query during compile time, but we can also make it return the query as a string. Fine. Oh, and yes, of course, there's the ceremony we need to do, implicit, qctx, quote, context, blah, 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 and then import, blah, 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 blah. And then let's say, let's quote foo, and let's just return foo for now. Okay, now, what do we have here? We have a expr of quoted of query. Okay, well, how do we pull out the tree from quoted? Well, we sort of did that in the parser, right? In the parser, we kind of said, okay, if we are a quoted, then we can pull out the tree. Okay. Well, we don't need a fully fledged parser inside of the run function. We can kind of get away with something simplified. Sorry, question?
I don't know. I didn't hear anything.
Okay. Yeah, so we could implement a whole parser in here, but we kind of don't need to. all that we need here is that we need this, let's see, quoted dot unquote. We might need that, but really, we don't need anything else. So, yeah. Okay. Cannot say run the tree. Okay, we can just copy this code, sort of. But, okay, we need an unlifter. Right? We need an unlifter to be able to unlift the syntax tree. So now we gotta copy a whole unlifter. Okay, well, there's a slight problem, right? We probably don't want to copy this whole code, especially as this gets really, really big. What do we do then if we need an unlifter? Okay. Okay. How do we deal with that? Well, can we just move the unlifter out? What happens if we move the unlifter out? Okay, that's a problem, because notice how the unlifter uses QCTX, and all of these things were actually imported from this quoted context QCTX thingy that we had here. Whoops! That's a bit of a problem, right? We need a quoted context here, okay? Okay. So, right, in Scala, you can do an import from a variable. How do we take care of that? Well, there are ways. There are ways to do that. The simplest way to do it is the following. Instead of an object, you make it into a class. The class will take the quote context. Make it implicit. And then, once it takes the quote context, it will import everything from it. Okay? Let's see. What other problems do we have? Oh, we need some variables. Wait, no, hold on. That's fine. Too many arguments for unlifter, blah, 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 blah. Oh, right. Well, this thing now is calling the supply function, but now this is a class, so obviously doing that, which is what this thing really is doing, is not working anymore because this needs to take an argument. Right now, it has to be new unlifter of QCTX, and that's how it works. But we don't actually need to do that, right? We're inside of here, so we can just call the apply function. Okay, apply. Okay, fine. So, where are we at? We have this unlifter here, and now we need to use it in here. So, okay, how do we use it in here? Well, let's declare it. Val unlifter equals to new unlifter QCTX. Well, technically it's implicit, so you don't even need to pass it in. Import unlifter dot underscore, okay. And then unlifter dot apply, or you could do just that, but let's keep apply there for the sake of clarity. Okay, so now we have an unlifter that we've abstracted out, and hopefully we can do the same darn thing up here. Right, unlifter.apply, and now we have an unlifter. A couple of other things like unsealing. Okay, we kind of relied on this function called unseal. Where is unseal? Oh, it's this object that's defined here. Can we move this out? Let's see. Ooh, again, this thing, they kind of rely on stuff. They kind of rely on, again, imports that came from this variable right here. So how do we do that? And unseal is an object with an unapply. Okay, well, let's kind of use the same pattern, right? In this case, let's create class utils, or let's say unseal util. And that will pass a QCTX, implicit QCTX, quote, context, la la la. It'll take an implicit variable, la la la. And okay, and then of course it'll have to do these wonderful imports. Some more ceremony. Okay, how are we doing here? Non-private method apply refers to private val QCTX. Okay, now we get into the wonderful issue of private versus public variables. We do val, that should fix the problem, I think. Val unseal util equals to new unseal util. Again, you can pass it in, but it should be implicit. Oops, new unseal util. Unseal util. And we can do import this. And we can do a blanket import. And we should be able to do that there as well. Okay. And okay. QCT. What? Okay. Well, now the plot gets thicker because QCTX is a variable that was inside of unseal util, and we declared it as a value, which is the same thing effectively as doing that. Right? This was a value that existed in this class, and now because in this class we have this thing, which is a value, when we imported unseal util as part of this import, QCTX was imported as well. And that's why it's complaining and saying, oh no, over here we don't know which one you used. Well, one quick way of doing that is to do QCTX inside of here. Import it as null or nothing. You can change its name, by the way. You can do QCTX as QCTXY, but we don't actually need to use this thing. So, okay, we can just nullify it. That's fine. So, oh, yes, and let's get rid of this because that's actually a syntax here. Okay, what's next? Okay, unseal not found. Ooh, the plot thickens. The unlifter needs to have a reference to the unseal. Okay, so now the unlifter needs to have an unseal util. Isn't it fun to watch how, as a result of so little, the complexity that we need to suddenly have just goes up and up and up and up? This is the definition of incidental complexity. All of the complexity that we've just created is more or less just incidental. But anyway, okay, blah, 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 blah. Okay, let's try compiling now. Okay. Oh, right. Where is QCTX? QCTX, again, because QCTX was here, and Parser is here, and unseal util has a QCTX, right, that we defined because we called it val. If it wouldn't have val like that, it would be perfectly fine, but oh no, it's an actual value that exists inside. So again, QCTX goes to nothing. Let's nullify it there. Let's see if we can do better. Yay, it compiled. Okay, so we have successfully refactored out the unlifter and the unseal. Okay. At the cost of much confusion. And again, all this
and
happens...
complexity.
I'm sorry?
And complexity.
And complexity. All this happens because this quoted context thingy is a variable from which we need to do imports. And that's why trying to abstract this thing away is so frickin' complex and annoying. Okay, fine. So now we have, this is not really a parser, this is a, let's call it a quote parser, quoted block, it's not even a parser, it just takes a quoted block and pulls something out. So it's a quoted block, whatever, quoted block, puller, whatever. Quoted block puller. Okay, so let's use the quoted block puller to pull out the quoted block from this quotative query. Dot AST parse, right? Okay, fine. Let's just not rename this function here. And AST parse, Q. Okay. Here's our syntax tree. And for now, let's just print it to make sure that we're sane. Print line, let's say pprint y to AST. Let's just compile this thing. And la 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 la. Okay. Good. Wait, no, hold on. That's not what I wanted. Where is it printing my... Oh, right. We haven't called it. We actually have not called our run function. That's what we sort of need to do in order for it to print the tree. And let's actually do that. Okay. Let us call run of Q2. La 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 la. What happened here? Okay, looks like our cannot run the tree. La 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 la. Looks like it did not like what happened. Cannot run the tree. Why did this thing fail? Why did it fail? And now, since I have this code formatter here, I had to actually manually add object foo. It's kind of annoying because otherwise the formatter doesn't work because it requires the outer thing to be an object. That's why the thing is there. Okay, let's try this again. Okay. Now okay, there we go. Cannot run the tree. Why can we not run the tree? We have a quoted dot apply of stuff, and then it's typed, so there's a type. Oh, that's right. Wait, what happened? Okay. Oh, that's right. We forgot that we always need to do, let's say, q raw. Right, val q equals to dot blah 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 dot unseal dot underlying argument Unseal. Yes. Right, we need to do that thingy, right? Because I just noticed that... Oh, come on, where's my terminal? Terminal? What happened to my terminal? Blah, blah, blah. Okay, my terminal just tweaked.
Hmm.
And now I need to restart VS Code, I suppose. Wait, can I launch a new terminal? No. Terminal. Okay. Kill terminal. Ah, so, but how did I know there was something wrong here? How did I know there was something wrong here? Oh, right. Q. Come on. No. There we go. Notice how I looked. Okay, everything here looks fine.
Yep.
Oh, wait, hold on. Oh, there we go. There's the thing. I'm investigating. Yeah, there we go. Use simple filter. Right. Okay, everything here sort of looks fine. Right. Query, and then applying two filters. Is sober, is Russian, is human, respectively, right? That's what I sort of did here, right? Originally is sober, then added is Russian, then added is human, and then finally passed this thing into the run function, so they should all be spliced in. That kind of works, right? It's entity of person, list of nothing. It should be list of string, but okay, fine. I'm willing to let that pass. There's a type ascription here, so that looks right. Oh, wait, no, there's an inline. There are inline blocks everywhere. I don't want that. How do I get rid of inline? I get rid of inline using unseal underlying argument. More ceremony. Just something you have to remember. Unseal underlying argument gets rid of inline blocks. Although I've done most of that work for you in general. So let's compile again. La la. Yay! And look, we even printed out our AST. Let's actually add something to delineate it. Blah, blah, blah. Okay, yay, printing AST. Oh, no, not there. Yes. Okay, there. So there's our AST, right? So we're printing a... Let's do that one more time. Okay. A filter, right? Is sober, is Russian, is human. Okay. So we have what have we done now? We have passed our syntax tree during compile time from here, printed out here, but from here, and then we passed it into here. And then from here, we took it, put it into here, and passed it into here, and from here we passed it into the run function, and we have reconstructed it in the run function. And oh, and by the way, this is now proper Quill AST, and if you want to take a look, right, here it is. It's proper Quill AST. Now, let's see if we can get Quill to make a query out of it for us. Well, okay. How do we do that? And now a bunch of stuff that I will just do very quickly that you guys are not going to have to look at. But I'll go through it super quickly. Blah, 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 mirror context. In this case, let's just do mirror dialect. Mirror SQL dialect. Let's just use this. And let's just use Postgres. There are multiple dialects in Quill. Again, in our toy example, we're only going to use Postgres, but in the regular Quill, you can specify what kind of database dialect you want. Again, we're not going to care about this so much here. New Postgres dialect. It's going to be IO, Quill, Postgres dialect. And what we're going to do here, and this is the super methods defined here, is going to be translate. Here's our translate function. We then call dialect.translate. Oh, look at that. It now even has decent autocomplete sometimes. Translate on the syntax tree, which is our AST that we've just gotten. Oh, and now we need a naming strategy. Again, we can specify it implicitly, but we'll just specify this one implicitly. Or we'll specify it explicitly again, because we don't really care for this example. Let's say lib get quill literal naming strategy val ast stnt. Oh wait, yes, that's what translate will return for us. What is this complaining about? Oh yes, AST2. We don't care about. Actually, we don't care. This does some additional stuff with the syntax tree. We actually don't care what it is. All that we need to do at this point is blah 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 is call statement dot. What is this? Is it toString? What is the thing that, yes, that toString. And that's our query! Yay! That's our SQL. We can return it from our function, right? We can actually lift this thing into a return value. Right, if we want to put expert inside here, we have to put it into brackets here. Wrong bracket. Right, but there we go. But again, if it's expr of SQL and we're just wrapping it inside of one of these, right, really that's the same thing as just doing that. Right? If we actually want to do something with it, like say, length, or do something with that value inside or whatever, then we need to do that. But in this case, we're not. So all we need to do is return that. right? Because this will return an expr string, right? So we don't. Does that make sense? Yes, no?
I think so.
Okay. So we're going to return it, but again, let's just print it during compile time to know that we are done, or we managed to produce it. Hurrah, we have SQL plus SQL. Compile. Hurrah, we have SQL. Would you look at that? We have actually produced SQL. So between the time that I called dialect.translate and toString, this is the entire Quill abstract syntax tree normalization transformation stack. Because translate is inside of Quill, and what the translate function does is SQL idiom. What the translate function does is it calls the AST normalization, which causes this large series of steps, and this is essentially the query compiler. So the translate function calls the query compiler that compiles the query or transforms the AST and then tokenizes it. So all of that just happened inside of these two steps. Again, between Quill Dotty and old Quill, this is not changing at all. And everything that's going on in here is being imported via this Quill SQL portable library. That's all coming in through here. So none of this actually needs to be rewritten. The entire transformation stack remains as is. All that we have to do is parse a proper AST, and voila, we have SQL. So there it is. We have now produced it. So now we are in real SQL producing land. Any questions before I go on?
No?
No questions at all.
Nope. Although I do have a question I've been thinking of. At one point, could you go over making a little kind of like syntax cheat sheet for us, so that when we actually start applying all this, we'll have something to just glance at to know how to apply certain things?
That's a really good idea.
Like,
I haven't thought of that. That's a really good idea.
yeah, and when you make it, you can explain like the importance of all of it again too.
That's a really good
Like
idea.
Thank you.
So here's the thing: I don't know half of it.
Okay. Well, I mean, it's not something that needs to happen now. It's something you can think of and write down on a notepad the things you want us to have on the cheat sheet and always add to it later.
Yeah,
you
so
can make
exactly.
a Google Doc that you can modify.
It's actually what I want to do. I think the first step of starting to write this code is going to be everybody goes and just I've already written actually everybody's going to choose some kind of one or two constructs to just print out and look at their syntax tree and play around with it. And I think the first step is that we will sort of put together on the Discord. We'll make a new section called syntax tree examples, and everybody will look at one kind of syntax tree and paste an example there with a couple of variations, and we'll put it together. I will make some common ones. I'll start with some common ones and then assign other ones to group members. I think because there are a bunch of them, and if we do them together and play around with them together, it'll go a lot faster.
Nice.
Yeah, so I think that's what I think we have that in the cards on the project plan or whatnot. That is the next logical step.
We do.
Um,
Okay.
Speaking of which, so the next any other questions before that?
No, I don't think so.
Okay. All right. So the next thing I want to go into is this is actually going to be more back to the parser where we're aiming to go. La 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 la. What I want to do is the following. Oh, wait. What? Oh, right. Just the query of parser. U1.ast. What I want to do is the following. Let's figure out how to print this thing, or let's figure out how to parse this thing. Right? We haven't quite done that yet. We haven't quite parsed binary operations yet. So let's figure out how we can do that. So okay, so this is actually the first example of how you do things like this in the parser. So let's take a look at the old implementation of the binary operation parser. So here's parsing. Here's parsing. Binary operation. Okay. We have this operation parser, which is kind of complex, or there's our operation parser, and it has all sorts of different clauses here, and it has all sorts of interesting things here. Okay? So we have this equality and dot equals, and we sort of kind of have equal on just about anything and not equal on just about anything. Ooh, numeric option ops. Guess what this is?
Like the regular operators usually.
Guess again? But it's close, actually. It's, this is an implicit class, like arrow-assoc. Pack.extras. This is just an implicit class that can go on different kinds of things. Anyway, that's fine. We don't need to go into that now. Reg ops. So this is like, all of these things are implicit classes that have been tacked on to various kinds of types. But let's see if we can do something like this. So, okay, quality operation, right? We're parsing. This is parsing now. So, a parsing we will go, a parsing we will go. Hoo ho ho ho, a parsing we will go. Anyway, so we need to, oh wait, hold on, find the unlifter. We need to go to the parser. Parser. And again, the real parser is more complex than this because I want to, in the real parser, I want to support user customization, which again adds a whole lot of complexity. But anyway, so let's say we do something like case. Let's just put null here for a second. let's say A equal to B, or A, again, that's the same darn thing. But again, it will complain. Because, right, you can't just do untyped things. Type must be fully defined. Whoopsie. Problematic. You can't just do equal on anything because it needs to be a typed API. Now, by the way, doing something like any, if you do it like that, will only work if A is actually typed as any. So that doesn't actually work, right? And you can't do an arbitrary type because that will run forever, and that won't work either. I'm wondering if I should file that as a bug. Anyway, you can't do that either. The only way that you can do something like this is you have to drop down to the unsealed API. And you have to do something in here, right? You have to do something like, let's say, select of, let's say, some kind of, I don't know, some kind of literal, and then something like inside here, right? This is going to be A, and then this thing here, and then in here, it's going to be something like equal, and then this is going to be an apply this on B. How the heck is this supposed to look? Well, I don't know off the top of my head, which is why, guess what? Print it out. So let's go to our printing function, or let's make a new one. Use simple quill 4. Rename use simple quill 4. Okay. And what are we trying to figure out? We're trying to figure out what something in line Q equals to A, in line def Q equals to A. Let's say val A int equals to 1, val B int equals to 2, A equal to 1. What does that look like? Oh, wait, hold on. Whoops, val Q. Oh, and we don't need any of this stuff. Oh, and by the way, or again, we have to print it, otherwise it might not show us anything because it might just be blocked out. By the way, if you're just doing something super simple like this, you don't actually have to do that, right? You could just stick them into here directly. A equal to B, or A equal to 1. Let's do A equal to B. Right? You don't actually have to put it into an inline and then put that inline in a macro. You just put it directly in. Anyway, let's compile it. Oh wait, we're compiling 2 files. Probably because we changed something. Let's see what happens. La la la. Oh wait, no, hold on. We're good. We're good. Oh, unbound identifier Q. Oh right, because we actually removed this variable here. We can't print it because it doesn't exist, and you can't print something that doesn't exist. Well, that makes sense. Let's see. Okay, there we are. Oh, interesting. Just passing it to the print macro alone won't make the compiler remove these statements. Okay, that's good. Ah, okay, sorry. It printed out everything that we had there before, so let's add a comment. Just recompile this because it was recompiling that too. Okay, good. Well, okay, that's roughly the syntax tree that we need to have. There it is right there. Ooh, but wait a minute. Actually, if you want to know what constructs you legit need to have in order to match a tree, well, anybody remember what we used? Where's print mac defined? Printing macro. If you actually want to know what legit constructs you need to use, well, for that, what you do is this. You do la 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 la, and then you do dot what was this? Show extractors, right? Long version and extractors. Right? What this does is this will actually give you the string representing exactly what you need to match to get a particular kind of statement. In other words, what you need to match when you get the thing that you're passing into this print mac function. So let's just look at this again. This print mac is used in so many places. Tons of other stuff has to recompile, which is why we were seeing trees from other things. But anyway, okay, so la 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 la. This is what we actually need to match. A little different from what the pprint.apply will show us. Pprint.apply will show us this. What we actually need to match on is this. Oh, and it'll print us extractors from all sorts of other stuff that we've done, like this, how we match an arrow function that we did up here. Well, this is the AST that represents an arrow function. It's a giant blob of AST that is very big. But oh, what happens if we take the code formatter? Let's see what happens if we take the code formatter and apply it. And again, we're going to get a redundant object thingy around it, but we don't care. Okay. What happened here? Oh, no. You couldn't. Expected class or object definition. And that didn't work. Oh, wait, hold on. Yes, we need to add this stupid object foo around it. Yes. Voila. Because the formatter, again, the formatter relies on the whole code block that you're passing into the code formatter.apply being proper Scala, and it's only proper Scala if you wrap it around an external object. Okay. La 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 la. Okay, yes. It's inside that. Okay, apply. Same thing. Ooh, look at that. If you want to match this whole long thing here, this arrow association, let's see what you need to have. Okay, this actually kind of makes sense. Select apply, type apply of arrow association. This is just some other type stuff. Ooh, list select one, list inferred, blah, 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 blah. So that's actually kind of cool. You can use show extractors and then pass that inside the code formatter. That occurred to me literally 5 seconds ago. That's kind of cool. That's kind of cool that you can do that. I did not know that you could do that. Neat. Neat. That is really neat. Definitely something to put in a slide at some point in time for some presentation. Anyway, so this is what we need to match on. Oh, A and B, except for the fact that we don't care, we don't want them to have to be, like, physical. We don't care about the name of the identifier. It could be any identifier, so long as it's an identifier. Ooh, but what if someone does something like blah? Right? That's a literal. Oh, wait. What happened here? Oh, wait, no, hold on. Sorry, these aren't strings. These are ints. So what happens if somebody uses an int there? Okay. So that's going to be a select of a literal. Okay. So actually, we don't necessarily want to force them to be identifiers. What happens if we do that? What happens? What will the compiler do? Ah, the compiler knows that it can internally compare numbers, which means it'll return false. See that?
Yeah.
But anyway, so what we can do is it's going to be approximately like this, but let's go back to the parser. La 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 la. So what do we want? We want unseal, apply, select, constant, except for the fact that this isn't necessarily a literal or a constant because it can be an identifier. But we can work with that because we can parse an identifier. Can we parse an identifier? Oh, we need to be able to just parse a plain old identifier. We have t-ident here, right? This is like t-ident. This is t-ident. We have a literal, but also you can have, right? This can be an identifier. Okay. La. Select. Oh, whoops. I get that. Select equal from. What was this? Select equal. No, apply. Select. Okay, literal of constant. Okay, so this. Okay, let's paste exactly what this variation of it was. Let's paste exactly what this variation of it was. Okay. And what? Oh, yes, constant, because constant is a term that means multiple things, so we use t-constant. And ident could mean multiple things, right? So we renamed it up here, t-ident. And found equal string, required tasty.symbol. And okay, this is probably not true. So this should be fine. Let's just try to compile it. We won't try to match it, but let's at least see if it compiles. Because obviously if it returns null, it'll screw everything up. So, oh, no. No, we can't just do that. We can't just do that. Ident, constant. This is... So this isn't right. Apply, select, literal, constant, list, ident, B. Is show extractors wrong? This is, okay, select, apply, reflection, symbol.
I will be right back.
Okay, cool. Hopefully I'll figure this out by then. Unseal. Seal. Okay. Or Where's the other unseals that we have? Okay, we have unseal here, we have unseal here. It doesn't like equal equal because it needs a symbol. Does that mean that show extractors is wrong? What if we do that? No. Select literal constant equal equal to. And this is also wonky. And this is also wonky. Let's see. Let's see. Equal equal to B. I wonder which... Am I using the wrong select? Apply of select. Selection term ref. What happens if I make them strings? What happens if I make them strings? Same thing. Interesting. Are there potentially some implicits that I need to pull in? No, I don't think so.
I'm back.
Okay, cool. One second, I don't remember how I solved. Let me just double check. Wonder if this is a bug inside. This definitely looks like it's a bug inside of show extractors, because show extractors should work. The exact extractors that I should be using should be shown by them. So this definitely looks like it's a bug of some kind. Let's see, what did we do here? Binary operations, select. Oh, okay. 1 second. Where's equal equal? So I have, where do I have equivalence? Apply, select, seal. No, but that shouldn't even matter. I should be able to select an arbitrary thing from my unsealed method. I should be able to select an arbitrary thing from my unsealed method. So this is, what select is this? qctx.tasty.select. What select is this? This.qctx.tasty.select. qctx.tasty.symbol. Did I import some special thing here? No, I didn't. So this is interesting. This is like a situation where you need to improvise a little bit. So let's call this symbol, and let's pull this out. That should work. And let's just call that that. Let's see what happens now when we compile it. Let's see, what's happening now? Oh, not found sim. Oh, I know what's happening. We forgot to do that. Right, okay, we forgot to do that. Right, because to go to unseal, you need to escape this quoted format. You do that with a $sign. But in fact, if unseal is at the top level, again, you don't need that. Oopsie. Okay. So normally this kind of, in some situations, it's going to require you not only to have a custom printing macro, but sometimes you're going to have to write something like a custom parsing macro. And that's just a reality of life. So what's going to happen sometimes is that you need to do something like object parse mac, and then inline, let's say, any can make it return units, and then let's say, oops, this is an object. Right, and then you're going to have parse impl, and then pass any inside of there. We'll just copy that. Parse impl. And then what happens is that you can actually go ahead and parse this thing and try different ways of parsing it. So any match, and if we want to import, in this case, we can import the unlifter. Do we want to import the the unseal util, because that will give us the unseal function. Again, we just copy the code, but fine, why not reuse it? So any match case. Unseal. And then let's do la 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 la. What do we have here? Let's just copy this whole thing. Right. Case unseal. And then you can match on this thing. Not d constant. We can rename it here. We can rename ident here. Println. Yay, it matches. Case otherwise. Println. No, it does not match. Oh, and if it doesn't match, it would be nice to be able to have a formatted code of the syntax tree. Or we could just pass it print mac. No, it does not match. Let's show it anyway. And then la 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 la. All right, and we need to return. We need to return. Return unit. And then we can just call printmac.printimple. Oh wait, can we? Oh yes, we can. We can call printmac.imple. We should be able to call it right because QCDX is implicit, so it'd be plugged in from here to here if we would call this thing from here. So we should be able to just pass, right? This is any that we're passing inside. And again, you could do O here and then pass this O inside, but again, we don't need an extra variable. So okay, fine, print it. Otherwise, yay, it matches. Okay. Okay, so then we know if it matches this kind of expression, then let's say we could print out B. B is. Or something like that. And then we could do, let's say, show. Excuse me, what is B in this case? B,
Bless you.
B is going to be, B is just a string in this case. Okay. All right, so now what we could do is we can actually, instead of print mac, we could do parse mac. Right, and this is like a custom parsing thingy. What is this? Unseal. We have unseal util. Unseal util. Unseal util. Oh, DSL. Import parseMac, import a new DSL.unsealUtil. Actually, that shouldn't go into DSL, but whatever. Okay, int required string. Oh, right. Bar. Actually, let's do int. And int 1, 2. No, come on. Compile. No, it does not match. Okay. Okay. Yes. Wonderful. We only want to recompile this because we only want to see the printout from that. No, it does not match. Let's show it anyway. Okay, so it didn't match. It looks like it didn't match this expression that we wanted to get. Okay, why did it not match? We have the extractors. No, it does not match. Let's show it anyway. The extractors apply literal constant equal equal. Why did it not match? Why did it not match? Parse Mac. Could it be? Oh, wait. Parse expression. Okay. Parsed expression.show some replaces. Ooh, underlying argument. Remember that we're doing underlying argument. Okay, well, in this case, we don't want to do underlying argument. We just want to do the expression, right? Because underlying argument is not something we want to automatically do. Otherwise, this thing here, if we do underlying argument here, any kind of stuff that we've passed into here, i.e. the stuff that we've passed into here, any inline blocks that we may have had will all be collapsed and we won't have the right tree that we're supposed to match. Okay. But haha, look at that. There's an inline block. There's an inline block that we forgot to get rid of. So, okay, in our parse Mac, we should probably, right, because this is a custom parsing, this is like a custom parsing macro that we're just writing to play around with stuff, right? So let's use the same pattern that we did before. Any raw val any equals to any raw dot unseal dot underlying argument. And then what we typically want to do in this case is seal it back up so that we can match it in here and we can use unseal together with that nice little quoted syntax here, right? Otherwise, if we don't seal it back up, we just have to match it with the stuff that's inside there, okay? Okay, did I miss a parenthesis somewhere? Any raw. Oh, I missed a parenthesis right there. Okay. Okay, well, now it had to rerun all the code because it had to recompile the entire printing macro.scala file, which included the print mac parse, which included, the print mac file, which every other thing in here contained, which is why you're seeing a giant thing here, which is actually why it's probably a darn good idea to take the parsing macro and to make it into a different file. Parsing macro. Actually, we should do parse mac, just to be consistent. This is why one of those things, like, you have to remember the fact that the way that Scala is compiled is one file at a time. You change the file, the entire file is recompiled. If any other code downstream uses anything in that file, that code downstream will also be recompiled because it has a dependency. Just something that you need to remember. Anyway, so So that's fine. We can. Oh, so now it's going to recompile again, printing macro, because again we've removed parse mac from there, which has to again recompile all the code yet again. Okay, whatever. We don't care about any of that right now. Blah, blah, blah. Compile. Yay, it matches. Right? So this is how you write a basic parsing macro. This is the best way to explore different kind of ways to match things. You write your own parsing macro, and you just try different stuff. And it's a lot of it is trial and error. So, okay, in this case, what we were trying to do is we were trying to match arbitrary expressions. So we wanted to do something like select equal equal from an arbitrary expression A and an arbitrary expression B. Arbitrary A and arbitrary B. So A is A and B is B. So we could do P dot apply A apply B. Now, let's try this again. Oh, also notice that the world wasn't recompiled right now because only one thing actually using parsing macro, which is your file here. But more importantly, look at that. When we passed 1, 1, 2, 3 here on the other, right on this side, and B on this side, look at that. Literal of 1, 1, 2, 3, ident of B. Ha! Good times. Right? Does that make sense? So our matcher is actually matching correctly, and it's pulling out stuff correctly. Ident A, ident B. Yay! Good stuff. Yeah, we're actually, this expression is actually working. This is how we can do equal equal. Okay. So let's put that into our parser. Before we do that, any questions?
No.
Okay. Where is our parser? Let's go back to our parser. And there's a lot here. This thing grew really quickly. Okay, voila. Okay, now we have this wonderful thing that we've parsed like that. Okay. Okay. And what? And well, now we want to have our binary operation. Binary operation. How do we? Binary operation. Like that. Where's the equal equal again? Okay. Now, let's just do it the simple way. La la la. Okay, string binary operation. Oh, wait a minute. What's A and B? A is a term. B is a term. A could be an entity. A could be a property. A could be a whole bunch of different things. That means that we have to pass A back into the AST parser. Okay. We have to pass A back to the AST parser. And we have to pass B back to the AST parser. Right? So before we call binary operation, for a second. A val A AST equals to, or let's say, yeah, equals to AST parse A. Ooh, wait, we can't do that because A is a term, not an expression. How do you go from a term back to an expression? Thoughts?
With a an unpacker.
Repack it.
No.
There's unseal. What's the opposite of unseal?
A sealer.
Sealer.
Or a pack.
Dot seal. Val B AST equals to AST parse B dot seal. So we seal them back up. Now we have AAST and BAST. And, okay. But here's the thing. We kind of have to do this sort of operation. Well, I mean, we can do this. Right? We can do AST parse dot seal. If we are enterprising, we can also do something like object seal, which has an unapply, takes a term, returns an option of an expression of any, and does sum of term dot seal. And then what you can do is then you can do directly in here seal it back up, which means you can just do that. I don't know, is that less confusing or more confusing? Maybe that's more confusing. I do have seal inside of my code base. I actually don't know if that's better or worse, but you can do that. I don't know, is that better or worse?
I have no idea.
Okay. Yeah, I don't know. I don't know if it's better or worse. Anyway, we could leave it like this for now. So, okay, then we have AAST and BAST. So now we declare a binary operation. We put AAST, and then, let's see, string operator, it's going to be AST dot equality operator. Equality operator dot equal. And then B, AST. That works. Again, in the actual parser, it's going to be pretty darn compact. It's going to look like that. Again, otherwise the parser will, just the code base will be enormous. So it's like that. Okay, so we have an equal operator. So let's just make sure that this thing compiles. Okay. So now let's look at this, our main code base. So let's give our person a name. And then we could do p.name equal to Joe. So let's compile again. Oh, wait, no, hold on. We screwed up here. Okay. Cannot parse Joe. We have not added. So, okay, so this expression worked, but our parser cannot parse string literals, right? Cannot parse the tree, string literal. Okay. So we have to parse a string literal. again, we kind of want to, it would be nice to have the, it would be nice to have the show extractors.
Are you retarded?
So, let's do use extractors, and we can do the code formatter in here. Expert.unseal.show extractors. So then it would tell us which extractors to actually use if we wanted to parse this thing. Wait, what happened here? Oh, cannot run the tree. I added this to the run function. Whoops! Oh, right, because this is the quoted block puller that I added to the write function. What I actually want to do is add this thing to the parser. There we go. Recompile. Okay. Literal of constant of something. Okay. Let's have literal of constant of something. La 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 la. Case unseal, right? Because this is a term level thing. Case unseal. And then constant str string, and then the Quill AST. The Quill AST, or excuse me, this is going to be t constant. The Quill AST has a constant, also constant construct like that. Now, by the way, another thing that you might see is instead of all of this, you might see just this. Is it const? I think it's const. Scala dot import Scala dot quoted dot matching. Yes. This, which comes from this package, is their implementation of that. So that's actually implemented in yet another package, because the Scala people that actually developed Scala needed to use this, needed to pull out literal strings so often they made a matcher for it. Just an FYI, you'll see that in places. Anyway, we can same as Scala dot quoted dot matchers dot const. Okay. So all right, fine. So we can pull out a constant now. Okay, good. Let's try to recompile. Ooh. Cannot lift constant. Cannot lift binary operation. We haven't added the clauses to the lifter and the unlifter for them. Gotta do that. Okay. Okay, let's make binary operation liftable. First, we have to make constant liftable. So, constant in the Quill AST is constant. Okay. Oh, ignore this part, please. It takes any. Any is not liftable, right? You can't lift any. That doesn't work. But we can assume the value inside is a string. Okay. It's going to have to be more complicated than that at some point, but we can assume that for now. Okay. Assuming the value inside of our constant is a string, well, then we could just lift it like this, right? Create a constant object, and then just use expert to lift the value. Good. Now, binary operation. Now, okay, so for now we're just gonna do A, B, and equality operator dot equal. Again, we're gonna have to do a lift for all the equality operators, but again, that's you know, we can do that, right? But the point is that you have a apply for binary operator that matches. Well, we can, I mean, the way that you do something like that, is like this: def lift. Where's this thing? Operators equality operator, right? So it's going to be def lift equality operator. Let's just say lift, and then it takes off, which is an equality operator, right? And then the way that this guy is going to work is it's going to say, okay, op match, la 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 la. Case. Oh, come on, how do I know that there's a way to do multiple cursors here. Ah. Shift, Control Shift. Alt? No. 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 Hold down Alt? No. Okay, whatever. I know that there's a way to do multiple cursors here. Anyway, quality operator dot not case la 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 quality operator. What is this? Quality operator, case object. Oh, extends binary operator. Wait, no, hold on. That's fine. Oh, yes, it did binary operator here. So quality operator extends binary operator, and case equality operator equal, case equality operator not equal. What did I do wrong here? Stable identifier, but equality operator equal is found. Wait. Oh, right. You can't do dot in here. So you have to actually, if you want to match on something that's inside of something, you actually have to import stuff. So, okay, fine. Let's actually import quality operator dot everything. So then we can do that. Is both defined an object lift transfer suitably and import. Wait, what? Okay. Null. Null. Let's comment that out. It is defined an object lifter. Reference to equal equal is ambiguous. It's defined as lifted. No, that makes no sense. Why is that complaining? Case the equal equal is ambiguous. It is defined an object and imported subsequently. How am I defining this in lifter? Reference to equal, okay. What happens if I do that? Stable identifier acquired, but this dot equal equal not found. What? There's a this dot equal equal? Okay, something is not adding up here. Why is this not working? If I just do that. No. What happens if I import this higher level? Oh, wait a minute. Is this... 1 second, let me just check. Let me just check something quickly. This is just a syntax thing that I don't remember. Case. 1 second. Why? I actually don't know why this is happening. It seems to be matching the wrong thing, and I don't know how come. What is op? Op is a binary operator. Okay, let's try this as off equal equal, and then let's do that. No, that didn't work. Let's just define it as op. Case op. Well, I guess that worked. EE. Let's define it as EE. And then do that as any. Okay, I guess that works. Oh, wait a minute, wait a minute, wait a minute. What if I go back to doing that? No, also doesn't work. Okay. Weird stuff! Anyway, just more trial and error, I guess. But anyway, okay, let's just do these two. Equal, equal, not equal. There are a whole bunch of other things. Oh, wait, no, here it is. Oh, there it is. There it is. Okay, quality operator dot equal equal or not equal or all of that stuff. Okay. Except that that should all be fine. Where is this coming from? The numeric operator, Boolean operator, string operator. So basically, there are a bunch of operators. Whole bunch of operators possible. So let's just import them all carte blanche. And then we could just do... we can just do... this is going to be equal equal. This is going to be not equal. And then can we do all the rest? Yay! We can do all the rest. So the point is... So the point is that for every single one of these, what we need to return is an expression of the equivalent one of these. So this is going to return an expression of a binary operator. How do you do that? Right? Well, the same way that we've lifted everything else. This is going to be equality operator dot equal equal. Equality operator dot not equal. And then all of these things that all need to be enumerated one by one by one by one. Come on, give me multiple cursors. 1 second. What are my keyboard shortcuts? Multi-line. No. Cursor. Add cursor above. Add cursor below. Control Shift Alt. Control Shift Alt. Yay! Voila! Voila! Control Shift Alt. Voila! This is going to be, these are going to be numeric operators. Numeric operator. And this is going to be dot. And each one is going to be its respective thing. And this is, except that this is not a numeric operator. This is a, what is this? Boolean operator. Boolean operator. Right? It's all in here. It's all in operator. Boolean operator. This guy, this guy. La 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 la. Oh yes, there's also Boolean operator, which is not. La. What are these going to be? There's also string operator. There are 3 binary string operators. Starts with, contains, and plus. So we're lifting all of our operators. String operator dot and its respective thing. Okay. Missing that. Boolean operator. What? Boolean operator dot exclamation point. Boolean operator. Oh wait, no, hold on. The exclamation point is not It's a prefix unary operator. We only care about binary operators. Contains is not a number of string operator. What is contains? Contains. It's binary operator. It's a set operator. Okay. Basically, what we have had to do is we have had to encapsulate every single thing that is a subclass of binary operator so that we could lift any binary operator. But whatever case, qcdx dot throw error not considering operator pop will add later lift binary operator. So now we have our lifter, we have our binary operation, we have A and B. This is going to be binary op. And then we have binary op. Expr is going to be lift of binary op. And so we have lifted our binary operator. What's wrong here? Found unit. Oh, yes. Op match. Expr of binary operator. Oh, right. That'll make it shut up. So, see, it thinks that because we've not returned anything from here like that, basically we're saying, okay, no, we're not returning anything. This whole part of the expression needs to return an expr of AST. Every single one of these cases needs to return an expr of AST. That's what this and all of them are doing. But of course, if we're not doing that, then it's complaining. Okay, fine. Give it all. The compiler will shut up for a second. Okay. Binary op expr. Val a expr. Apply. Right, we need to apply this recursively. A is going to be. Oh wait, hold on. Do we need to apply this recursively? Oh, yes. Right, we need to apply this recursively because we need an expression of AST. So apply recursively on A. B expr, apply recursively on B. And then, finally we create our binary operation. Binary operation. A expr. Binary op expr. B expr. Okay. Now we're getting somewhere. Oh, so we've done the lift. But now we need to do the unlift. So we need to translate all of this stuff back into the lifted thing. Right? So let's take this thing and let's take this thing and then this thing and do the equivalent unlift. Where's our unlifter? Unlift. Voila. Where's our unlifter? Here is our unlifter. And now instead of lift, it's going to be the mirror image of lift. It's going to be unlift. And in unlift, we're going to do exactly the opposite as we did in all of these cases above. Which means... Just change that error if it blows up. Let's see. And la la la. Oh, wait. We will do that one in a second. Do all of these. Lift. Unlift. Oh, we actually need to import all of these. Right, let's do that. Imports. Okay. Okay. Oh yes, and unlift has the opposite signature. We go from expr of binary operator back to binary operator. It is a mirror image. And then we just have to do these two. And what did we do wrong here? Boolean operator, numeric operator, set operator. What is plus? Plus is a string operator. Oh, we need to import string operator dot plus. And then we'll be able to match on it. Well, then we can just do that. That's fine. Now, more importantly, we need to... What is any? Not equal. We imported any is not equal. Weird. Yeah, and lifter and imported subsequently by import equality operator dot. Okay, fine. Whatever. Equality operator dot not equal. Doesn't matter at this point. Equal. Okay. Def lift. This is what we need to have there. Okay, good. Now, we need to have the mirror image of this. Mirror image of this in our unlifter. La 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 la. So, it is going to give us, we're going to match. Instead of returning this, we're going to match this. Okay. Now, instead of getting the expressions, we start with the expressions, and we need to get the actual terms. And then at the end, we will plug them into the binary operation that we reconstruct. Right, and this, at this point, it is normal code. A binary op and B. Okay? It's not apply on A, it's apply on A expression. Recursively apply on A expression, recursively apply on B expression, and unlift the giant thing that we just wrote on binary op expression. Let's see if this works. Wait. Value is not member of set operator. Oh, it's not set operator. What did I do here? Set operator. Oops, it's string operator. Excuse me. Oh, what did we? Cannot unlift the tree. Okay, so we've written our lifter, we've written our unlifter, and now we are going back to our query, and hopefully we can now lift and unlift the, we can now lift and unlift this equal expression after we've parsed it, right? And we need to lift and unlift it because this thing is going to be plugged into here, and then from here is going to go into here, and then from there it's going to go into there, right? And then to go back from here, you need to lift it, and then once you've plugged it in here, you need to unlift it, and then to return it back here, you need to lift it again, and then to plug it back in here, you need to unlift it. To bring it back here, you need to lift it, and then to bring it there, you need to unlift it. Okay. So we need to have an unlifter, right? So anything, the way to remember this is when you are going in, you lift, right? Lifting is about lifting things into a syntax tree. So when you, excuse me, I'm wrong. When you are going out, remember how we covered last time going out into the cold world, right? Going out into the cold world, you need to lift things. You need to lift things into the Scala syntax tree. You need to lift things up to go out into the cold world. To come back in, you need to unlift them. Maybe a metaphor would be like a flying car or a blimp or something. The cold world is very, very bad, so you need a blimp and you need to lift yourself up into a blimp. Or you need to lift your AST into something that flies and can stay off the ground because the earth is cruel and nasty and horrible and people are hunting each other to death and lots of terrible things are happening on the ground. So whenever you go out, you need to stay in the air. You need to be lifted. But then when you come back in, you need to be unlifted. Actually, a much simpler metaphor is just a coach, like mounting horses or something. You lift yourself up into a coach wagon or something like that so you can just get around on a horse. I think that's a better metaphor. Less dark. Anyway, sorry about that whole reverie. What is the problem here? We cannot lift. Why can we not lift? We can't, why can't, the thing that's printing, the thing that we can't lift is, whoops, I need to do AST.show. Wait, hold on. No, it's this. I can't unlift. I can't unlift. Let's go to the unlifter. Def unlift. What can I not unlift? Oh, my message is wrong. Or I should do oh, not that. What can I not unlift? Can't unlift the tree. Oh, right. Let's do unseal. Actually, let's do... Can we do can't unlift the tree? And then... let's copy our printing function. Let's copy our printing function. Again, we should really abstract this out, but I guess we'll do that later. Where's our unlift? Can't unlift. Not what I want. Cannot unlift. Cannot unlift the tree. Blah 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 blah. Blah 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 blah. Blah 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 blah. Cannot unlift the tree. This should give us a better idea of what the tree actually is that we cannot unlift. Aha, cannot unlift the tree. And what can we not unlift? We cannot unlift select ident of constant. Oh, whoops. We forgot to write the unlift of constant. That's an issue. Well, that's pretty easy. Case. All right, in this case, it's going to be unlift. Right, remember we did unlift, and then we did literal constant. We were just considering strings for now. Value, constant, value. Oh, yes, right, t constant, because constant is also part of AST, so we have to rename the one that's inside of qctx.tasty. And what else is this complaining about? Cannot find oh wait, what is wrong here? Not unlift, excuse me, unseal. Right? Unseal. Because we're just trying to get at the tree inside. Okay. Compile. Cannot unlift the tree. Select of, wait a minute. Apply selective ident constant dot apply. Ident. Oh. Right. Oops. Excuse me. This is constant from io.getQuill. This is io.getQuill.constant.apply, not constant.apply. I'm following the wrong methodology. Again, follow the methodology. Constant. Here's constant. This is lift. Unlift is the mirror image. Follow the methodology, and you shall be saved. Possibly. If you're lucky. I really have to stop it with the cynicism. Anyway, yes, there, right? Copy, paste, and then this is what we had. This is what we had, and then this is what we had from the lifter. Reverse it. Unlift does the mirror image of lift. Voila. Constant. There's an expression inside. Constant, again, this is io.getQuill.constant, and the expression inside, in this case, we're not lifting it. Now, this is going to be unseal, and this is going to be literal constant value string. There we go. That's what that's going to be. And again, if you're feeling bored of writing this whole gigantic thing, never fear. All you have to do is import io.getQuill, Scala.quoted matching, const. And then instead of this whole long thing here, all you have to do is const. Okay. So now we have constant. Oh, wait. What? What did I just do? Oh, oops. I put constant into ident, not into here. Oops. Okay, whatever. It's fine. We can live without it. Anybody still with me?
Kind of. Yeah, it is getting late.
Yeah, I know. It's 12:06, and I just went to hyperspeed. Okay, let's see if we can compile. What happened now? Can unlift. What can we unlift? Ah! Oh, yes, I have to do that. Apply. Come on. Ah. Constant apply. Show apply. Literal value. T constant. Come on. Ah! Finally. Select P.star from person aware, name equals Joe, and is Russian and is human. Yes! We have implemented binary operators and we can lift and unlift them as well. Yes! Parsing, where's our equal? Where's our equal string? Right. Now we can do more things like not equal, because we've already implemented this already. We've implemented this in the unapply. So now we could do person not equal to Joe. Yay! Oh wait, no, person, what? Person and equal to Joe. It's supposed to be not equal. Okay. Quality operator not equal. Def lift not equal. Def unlift equal, not equals to not equals to. Okay. How could this be the case? Our lifter is right, our unlifter is right. Okay. We have the correct lift, we have the correct unlift. Def lift. Where's our def lift? Okay. Okay. Binary op expression. That looks right. Not equal to. This should be working. Quality operator. Why is this? Oh, right. We did change it. We did change it. Why is it still equal? It should be not equal. Filter P. Seal not equal to unseal. What happened? Why is it equal to not equal? EE equal NE not equal. Left binary op expression. Binary op, lift the binary op. And our lifter equal is that. And our unlifter is that. I have no idea. Gonna have to check it out.
We lost someone.
Anyhow, I think we're just about done. Whew, we covered a whole crap ton tonight. We plugged in real Quill. We explored arrow function trees and
you were recording,
oh,
right?
Yeah. This thing is recorded.
Okay.
This is a lot. This is a lot. Yeah. So we've got We've got a full implementation of the run function working. We've instrumented a dialect. This has been a marathon. This has been a marathon. All right, guys. So let's call it a night, and next time we can finish this thing up, and please rewatch the parts of it that you might have missed, and I'll gladly answer any questions. But this is it. We're ready to go. All right. Have a good night then.
You too.
Good night.
All right.
Good night.
This is not working. Should be. This should be not equal. Parsing. Oh, what's the AST? Printing AST. Oh, AST is equal. What's the AST before? Okay. What was the first print Mac? First print Mac was... Oh, quality operator equal. So we parsed it as equal. Why did we parse it as equal? We parsed it wrong. Where's the parser? Equal, not equal. Unseal, seal of equal, unseal, seal of not equal. We are parsing it wrong. But how? Okay, what happens if we just blank that out? And let's force the recompile. What? Still equal. But I literally blanked out the clause in the parser. Okay, what if I blank out both clauses in the parser? What happens then? Yes. Oh, wait. Oh, there we go. Now it won't work. Oops. Not what I want. Okay, what if I add it back here? That. What? Extractors equal. Oh. Wait, no, hold on. No, that's oh. Oops. Wait. No, hold on. No, that's not it. There's my parser. If I blank both of them out, it fails. What happens if I do that? What happens if I do that? Okay, then it doesn't match. Okay, so it needs that to match. And the equality operator is not equal. Okay, let's change that. But it's still equality operator that equal. It gets swapped in. Am I lifting it wrong? It's got to be something in the lifter. Case EE. Equality operator equal is EE. Lift. Binary op expert. See what this is. Ah, okay. Oh wait, hold on. Let's just do binary op. Let's just check what the binary op is. Op. Aha, okay. So, I'm parsing it correctly. I'm just translating it into equal for some reason. So this is matching anything. Imaginably, if I would do this in front of it, then it would be the opposite. Yeah, okay, so it's matching anything. Weird. Don't know why it does that. Okay, you know what? Fine. If op equal to that. If op equal to that. Voila. Equals. And I have not equals. Okay. All right. So, good to go.